Hello, astronomy. So in class so far, we have talked a lot about stars. We talked a lot about how stars live and how they die. And we've also talked a lot about what they're made of. We know that our sun, for example, is made out of hydrogen and helium. That's because it's taking hydrogen and turning that into helium. And so our sun has a little bit of both in them. And then we talked about lots of other elements present in other stars and even in other nebula. But I think I've told you guys in class before, we've only been able to explore our solar system. We haven't really made it very far out of our solar system, and we can't really send any spacecraft to the sun. So how do we know what's inside the sun if we can't actually go there? That's the topic of today's discussion: is how do we know what stars are made of? Um, and we're going to be talking about that with atomic spectra. So atomic spectra. Let's just kind of break down those two words for a second. Get my laser pointer, I think. So atomic spectra, when I say the word atomic, that just means it's an adjective for atom, something to deal with atoms. Spectra is this plural for word spectrum. So spectrum is singular, spectra is more than one spectrum. And it just means many wavelengths of light. So wavelengths of light, what do we mean? What do I mean by that? So let's do a little bit of review. So if you guys remember last week, or perhaps the week before now, we talked about the electromagnetic spectrum. So the electromagnetic spectrum is basically light. It's every possible wavelength of light. And what color a light is, or what kind of light it is, depends on the wavelength of the light. So on this diagram in here, radio waves are the really long wavelengths, and as we go up, we have microwave, infrared light, and then finally visible light, the light that we can see. Then as we get smaller wavelengths or more energetic, we have ultraviolet light, X-rays, and then gamma rays. So the type of light you have depends on the wavelength of light. So why am I telling you this, and how does it help us determine the elements? Okay, well, we're getting there. So before we can talk about the type of elements that are in stars and how light tells us that, we need to understand a little bit about how light is produced and how we see light as it comes out of a star. And so to do that, we're going to talk about three types of atomic spectra. The first type is a continuous spectrum, or continuous spectra. So a continuous spectrum is something that's uninterrupted. So when I have a continuous spectrum, it's the entire rainbow. I have every single possible color in the rainbow, and actually every single type of light in the spectrum. Some of the pieces of light may be brighter than others, but that doesn't really matter. I have every single wavelength of light contained in a continuous spectrum. And a continuous spectrum comes from a hot source. So if I have a hot source like the sun or a light bulb, the light that it produces contains every single color in the rainbow. So this is kind of the simplest one to understand, is because all I have here is a hot source. The light is not passing through anything else. It's just passing through empty space to produce that continuous spectrum. Okay. Next type of atomic spectra is called an emission spectra. So now instead of having a hot source, I have a hot gas. So when I have just a gas by itself that is excited enough, it will glow. In fact, we know that anything that has heat glows. Usually they glow with continuous spectrum, but when I have just a hot gas, it glows with emission lines. So now emission lines, instead of having every single piece of the rainbow, I only have very small slivers of the rainbow. For example, this gas gives off a little bit of purple light, a little bit of blue light, green light, and then a little bit of red light. And that's it. But the thing about emission lines is that they help me understand what this gas is made of. So now we're getting a little bit closer to knowing, okay, now I understand how we can understand what elements are inside stars. So each element produces its own unique emission lines. It's kind of like how we have fingerprints, or we sign our name on a piece of paper. That fingerprint or that signature identifies who we are. Same with elements. When elements glow, they produce emission lines that identify exactly who they are. And how do we know this? Well, we have scientists have these things called emission tubes, and these emission tubes, they fill them with gas. So, for example, on this page, I have hydrogen, mercury, and oxygen. Now, mercury is usually a solid at a liquid at room temperature, but they brought this one up to a gas. And once I heat these gases up enough with the right kind of electricity, I can make them glow with emission lines. So here's hydrogen's emission lines. It glows in a little bit of purple, blue, a greenish blue, and red. So those 4 specific emission lines identify, oh, this is hydrogen, H2. Mercury has purple, green, orange, and has a tiny bit of red. It's kind of hard, it's kind of faint to see. So scientists know that those emission lines identify mercury. Oxygen has a lot of emission lines here. This is O2, by the way. And by the way, this hydrogen is not the same hydrogen we'd find in the sun. This is the more like the hydrogen we find in our atmosphere. Anyway, oxygen, I have O2, so some purple, some green, a little bit of yellow, lots of reds. So those emission lines identify oxygen. So remember, emission spectra is a hot gas that's glowing, and the light that it produces gives me slivers of the rainbow, not the entire thing, but just kind of slivers. And this is what happens inside nebula. So we didn't really talk about nebula that much, but nebula are just gas clouds left behind by stars that have died. So this is the Orion Nebula. And all this red stuff right here is emission spectra. This is probably hydrogen gas that's glowing. If you ever see a nebula that's blue or white, that is not actually gas glowing, but that's the nebula reflecting starlight. Whenever we see nebula, a lot of that gas is glowing with emission spectra. And when scientists look at that emission spectra, they through the right instruments, they can tell what elements are in that nebula. Okay, so the last type of atomic spectra, probably one of the most important for stars and actually planets, are called absorption spectra. So here is kind of last 2 types. We just had a single step process. This is kind of a 3-step process here. So we have a hot source of light. We already know that a hot source of light produces a continuous spectrum. So when I pass a continuous spectrum from a hot source through a cold gas, it produces absorption lines. So this is kind of the opposite of emission lines. Now I have absorption lines. But the thing about these absorption lines is that these absorption lines match up perfectly with the emission lines. So for example, if I took my gas from this first example and look at the emission lines right here. Actually, let me just kind of go forward a few slides. I'm trying not to confuse it too much. If I take this gas right here and look at the emission lines, and then I pass a continuous spectrum through it while it was cool instead of being hot, the emission lines line up perfectly with the absorption lines. So whatever emission lines a gas cloud will produce, it will produce the same emission lines if I pass a continuous spectrum through it. So now instead of light being emitted from the gas cloud is absorbing light. So even though I have every single color in the rainbow being produced here by the hot source, some of that rainbow, tiny slivers out of that rainbow, is being absorbed by the gas cloud. And well, how does it tell us what is inside stars? So if you guys remember, I know it was a while ago, we talked about layers of the sun. And remember, so our sun has inside layers and outside layers. Our sun basically has an atmosphere just like the Earth does. And the sun's atmosphere is cooler than the sun's surface. Now, it's still really, really hot. It's still hotter than anything we have on Earth except for lightning. But because the gas surrounding the sun is cooler than the surface, when we pass the sun's continuous spectrum through the atmosphere, it produces absorption lines. And these absorption lines, which again are pieces of the rainbow that have been absorbed by the atmosphere, tell us what the atmosphere is made of. So we can't really get a good idea of what the surface of the sun is made of, but by looking at what light comes out of the sun's atmosphere, we can tell what the sun's atmosphere is made of. And actually here, this is the sun's absorption spectra. So right now you're seeing the rainbow. This is the entire rainbow, except there's lots of shadows, lots of gaps here. And if you were to ask me what each one of these gaps were, I couldn't tell you. But I can tell you that hydrogen and helium have both been identified in here. But these gaps are more than just hydrogen and helium. So even though hydrogen and helium make up most of our sun, there's lots of minute elements in the sun, and many of them have not been identified yet. Scientists know what a lot of these gaps mean. They can tell what elements are inside the sun, but there's still many gaps that scientists don't know about. They're still being studied, and they're still trying to figure out, well, what is actually inside the sun? Is it a different element? Is it a different phenomenon? So that is how we know what our sun's atmosphere is made of. And we kind of use that information to discern what is inside the sun as well. So again, to sum up, when you have a hot source, it produces a continuous spectrum. It produces the entire rainbow. Whenever we look at the light from a hot source, like a light bulb or a star, we see continuous spectrum. Whenever we have a hot gas, it glows with emission lines. But for most stars and our sun, we'll have atmospheres. So when that hot continuous spectrum passes through its cooler gas or the cool atmosphere, it produces absorption lines, and those absorption lines are fingerprints for whatever gases or whatever elements are contained inside that star. So that is how we know about what is inside stars, not just our sun, but also stars that we see in the sky. Every star has its own set of absorption lines. And actually, we can also use this method when we look at what elements are on other planets. For example, when I was a kid, I remember, well, actually, no, even after I was a kid, back in 2012, Venus passed in front of the sun, which only happens every 100 years or so. And they used the absorption lines from Venus's atmosphere, because remember, what you have is you have a spectrum being passed through a cool gas. So spectrum passed through a cool gas like Venus's atmosphere, and they were able to determine the elements inside Venus's atmosphere. At that point they already had an idea. Back in 2012, they already had an idea of what was in Venus's atmosphere, but you can't really pass up the chance to look at the absorption spectrum again whenever nature gives you that chance. And actually, let me pause the video because I think I have a picture of that. But I finished the lecture already. If you need to stop here, by all means, you can stop here. I will say though, the next flip grid you guys are going to do, you guys are actually going to show me your own emission spectra and your own absorption spectra. So if you want a few instructions about that, stay tuned. So give me 1 second. All right, so I found the picture. I'm going to show you some of my amateur astronomy here. So let me show you my setup. So I took my binoculars, which I've since lost. It's kind of sad. I took my binoculars and I blocked out some of the sunlight. So I fed the sunlight in through the backwards. The reason I did that, oh no. Okay, the reason I did that is because the binoculars acted as a kind of like a projector. I projected the image of the sun onto this white wall outside my apartment building. And here's the projection. Here's the projection of that sun. You notice this little black dot right here? That's Venus. So Venus was passing in front of the sun, and there's a better picture right there. And actually, now that I remember this, what they did, what astronomers did was actually really crazy. So right here, this is Venus passing in front of the sun. It lasted about, I don't know, 6 hours, I think. Was really crazy. What they did is they actually observed the moonlight, because sunlight is so bright. They actually observed how the moonlight changed, because moonlight is just reflected sunlight. So part of Venus's absorption spectra was being projected onto the moon, and astronomers used the moon's light to determine the composition of Venus's atmosphere, or maybe confirm the composition of Venus's atmosphere, which is just really crazy for me to think about. I don't know why they wouldn't look directly at the sun or directly at Venus while the transit was going on. I don't know. But That's a really cool application of absorption spectra. We can use absorption spectra to see into the atmospheres of other planets. So every time a star passes behind a planet or the sun passes behind a planet, we can use that starlight to determine, well, what is this planet's atmosphere made of? And in fact, when Cassini was orbiting Saturn, Cassini could observe the stars throughout Saturn's atmosphere to determine the composition of Saturn's upper atmosphere. So when I talk this week and I say, hey, did you know that Jupiter and Saturn both are made of hydrogen and helium? That's why. That's how we know that, is because you can use absorption spectra with starlight, which is pretty amazing, to see what those atmospheres are made of. And we get all that absorption spectra, or we can confirm all those absorption spectra just by reproducing the same experiment in a lab. As long as we have the element somewhere on Earth, we can put it in one of those emission tubes and find the frequencies that those gases emit light in. Anyway, so stay tuned for a little bit later. I'm gonna give you guys, I think, what I'll do for your next flip grade. You guys will kind of do a mini lab to demonstrate your knowledge on this topic. And I will post my video on Flipgrid, kind of do a demonstration, and ask you guys to try something similar. Thanks for watching this lecture on atomic spectra, and y'all have a good day.